In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 1, Introduction, Part 6. Now we have been talking about the materials, behavior in the plastic regions, and now we have come to an interesting point. Of course, these slides that we have been considering and I have been presenting to you are in regard with this question: what kinds of plastic deformation are there? This figure shows the behavior of materials under various temperatures and also various strain rates. Okay, for instance, here we have 0.5 inch per minute. A strain rate is d epsilon over dt. So epsilon is dl over L, so it's dimensionless, and over time it's just per second or per minute. So here we have shown 0.05 inch per inch, which is dimensionless, and per minute. As you can see, the strain rate changes: 0.05, 10 inch per minute, 100 per minute, 19,000 per minute. This is a dynamic loading, and this is static loading. You can see that there is much difference between the behaviors. I will talk about the effect of a strain rate on the material behavior, but now I want to concentrate on the change in temperature and see how the change of temperature affects the material. Okay, one material at one strain rate. Now here we have the reduction of area, percentage reduction of area, and here we have the testing temperature. What material is it? It's BCT, thin intention. Okay, body-centered tetragonal, that is the crystal structure, BCT. Thin is a BCT, body-centered tetragonal. Now, thin intention, that means that we have a specimen made of tin and it's under tensile test. Now, what do we have here? Reduction of area percentage. Of course, for the tensile test, the original area is greater than the current area. So it's better to write the original area minus the current area divided by the original area. That's the percentage of reduction of area. Now that is the testing temperature. It means that we have tested this in tensile test at different temperatures. Strain rate is constant strain rate, and different temperatures. And we have obtained these points, and joining these points we have obtained this figure. Also, with different strain rates we have done these tests. So to make such a figure you need to do a lot of tests. Right, let's just consider one of them, this one, the first one. This one shows that here we have very little deformation, because reduction of area means deformation and it means ductility. Okay, so here is very brittle at low temperatures, but at higher temperatures it is very ductile, nearing 100% reduction of area, which is very strange. It means very high reduction of area. Okay, And we have this region like that. At certain temperatures, we suddenly change from a brittle material to a ductile material. So you can see here that it is better to consider the behavior of a material as ductile or brittle, rather than saying that this is brittle, that is ductile. Its behavior is ductile or brittle, because under different conditions it behaves differently. So here we say brittle to ductile transition is in a very short range of temperature. Yeah, for instance here, and it's about 20%. But if we increase the temperature, say to 155, then we get about 80. 150, we get about 60, and a bit more, we get about 80%. 155, we get about 90%. So in a very short range of temperature, about 20 to 30 to 40 degrees, around 150, we have a lot of change, a transition from brittle to ductile. Okay. Now if we look at different strain rates, we see the same behavior being repeated, except that this transition moves to the right. Okay, if you increase the strain rate, the transition temperature, or this range of transition temperature, changes, increases in fact. So here we could see the effect of a strain rate and temperature together. Okay, this transition temperature is very important because, for instance, some materials which have these transition temperatures, if you use them in a structure, if this structure, supposing is functioning in an area which we have various temperatures, yeah, or cold temperatures, then if the structure that we have made from this material functions at 150, then suddenly it changes its ductility. Supposing the temperature decreases about 20 degrees. If the temperature increases from 20 degrees, it becomes ductile. If it decreases, it becomes brittle. Here brittle, here ductile. Now let's go to a more near this tin, because its transition temperature is here. But for some mild steel, for instance, transition temperature is about minus 20 or minus 30. Then it's very dangerous, because if you use this structure in a place that is minus 20 or minus 30, then you will change from ductile to brittle. It means that there is a possibility that it might fracture. Okay, fractures in many ships which used to go around the world and go to the North Pole happened due to this transition temperature. Very famous incidents in the Second World War, where the ships were carrying arms from United States to Russia. On the way, a lot of ships were fractured from the middle. They fractured in two halves, and it was a catastrophic fracture. And the reason was this. The reason was that during the journey, the temperature changed. For instance, near the North Pole, to very low temperatures, and the transition temperature was met, and then the catastrophic failure happened. Okay, let's go and talk about toughness. Now, another property of the material which we are interested in is to do with the plastic deformation is toughness. What is toughness? Toughness is the area under the curve. If you draw the curve for a tensile test, area under the curve is toughness. Toughness is equivalent to energy and work, because the area under this curve, what is it? If you take a small element here, d epsilon, and you consider sigma at the epsilon, then the area of this element would be sigma times d epsilon. Okay, sigma times d epsilon. And sigma is F over A, and epsilon is dl over L. Therefore, F times dl is force times displacement, and it means that changing length, and it means, what is it? It's work, and work is energy. So the area under this curve is the energy, and we call it toughness. Why? Because it measures how tough a material is. For instance, this material is not so tough because it can absorb that amount of energy, and it will break high carbon steel. It's very strong, much stronger than this one. Yeah, because here SUT is about that much, here SUT is about that much, twice, almost twice as this, but it's much less tougher than this. If for instance, if you make part of a car with this material, another car with this material, if the car has an accident, this part will fracture very quickly, but this part will not fracture. What happens to it? It deforms and absorbs the energy. That's why in modern cars you see that the body panels are made of tough materials with high toughness, so that way when they impact, they have an accident, the material is deformed plastically, and the people in the car will not be injured. Okay, so in this case it's better to use a less strong material than a strong material, because here strength is no good, here toughness is good. So we understand what toughness is. This is low toughness, medium toughness, high toughness, because carbon, when we have a high percentage of carbon in the steel, it becomes very brittle, it loses ductility. Of course, ductility is different from toughness, because, for instance, look, if we have a rubber is very ductile, and we get a curve like that. Okay, it's twice as ductile as this, or many times more ductile than this, but the area under the curve is very small as compared to this. So ductility is different, toughness is different, toughness and strength are different. You should distinguish between these properties. Okay, all of the properties we can get from the tensile test, which is yield strength, modulus of elasticity, ultimate tensile strength, percentage elongation, percentage reduction of area, toughness, fracture strength, ductility. All of these have very, very special meanings, and you should understand very deeply what they mean. Okay, then let's have a look at some materials and their behavior. Right here again we have stress-strain curve. Now, martensitic, quench, and tempered. Now this is martensitic steel. Martensitic austenitic quench and temper. Martensitic austenitic is is a alloy steel. Ferritic austenitic also is an alloy steel. And here is the austenitic, that is an alloy steel as well, and ferritic. Now, these are all alloy steels. As you can see, martensitic, as expected, has the highest strength, and ferritic has the lowest strength. It's almost nearly 3 times as this. Yeah. All of these structures are obtained through heat treatment. So we can change the properties of a steel by heat treating it. Right, now HSLA, high strength low alloy steels. These are the alloys used in fact in the car panels. Very popular. Mild steel, this is mild steel, and this is high strength low alloy. Low alloy means that alloy components have smaller percentages. But as you can see, different alloys, 500, 570, etc., increase, although the alloy element has a very small percentage, but its effect is very impressive. As you can see, mild steel is about 200 megapascal yield strength, and this HSLA is more than 500. Yeah, almost 2.5, maybe more yield strength these alloys have as compared to mild steel. Now here we have compared very different materials. Aluminum oxide, which is a ceramic, and glass, which is also a ceramic. As you can see, these are elastic and suddenly breaks because there is no plastic deformation in ceramics. Most ceramics have no yield strength or ultimate strength. The fracture strength is everything. It yields here, the ultimate strength is here, and everything. But you can see different ceramics have different properties. Right, let's have a look. Let's make a comparison of these different materials. Like this is a brittle polymer, yeah, brittle polymer, like polycarbonate, ductile polymer, like polyethylene, and elastomer, okay, like the material used in tires. So you can see that here we have a lot of ductility, but as I said before, very small toughness, the area under the curve. But here the ductility is less than this, but the toughness is much higher. And here the toughness is very less because it's brittle, and ductility is much lower. So in the best material here is this one. Of course, if you compare steel to these materials, you will realize that steel is the best engineering material that you can use in design and manufacture. So far it's the best.